Okay, welcome back. Let's take a look at what we call constant cash flow projects or annuity projects. So what do we mean by this type of project? In general, they take on the form as shown in this cash flow diagram here. So if we're looking from a lender's perspective, for example, at t=0, they're going to have a negative cash flow, lending money to a borrower who is then going to give them back a series of payments of equal amounts. So when do we see this type of thing? We see it all over the place. So for example, we see it with mortgages, but we also see it with car loans. We see it also with what we call financial annuities, annuities due, etc. So let's take a look at how this all works for us. So what I'd like to do is get us a general equation that is going to help us out with these constant cash flow projects or annuity projects. So remember, for our general any kind of future cash flow case, we had an equation that looked like this, that the total present value of all the future cash flows for the project, we could also say was equal to CF0, the cash flow, the total cash flow of the project at t=0, and that was equal to each individual future cash flow first discounted back to t=0, just using the future value, present value formula. And then after you've done that for every future cash flow, then you add them up there. So if we have constant cash flows, then the CFI is going to be the same for every one of them. It's just going to be a constant like 2 or 3 times pi or something like that. So whenever that happens, we can pull it out of the summation sign. And when we do that, we get this. You see, it looks very similar to what we had above, but we've simplified it because the cash flow is constant. Every one of these future cash flows has the same magnitude. Because of that, we can pull that cash flow out of the summation and make our life a little bit easier. Also, when we have this type of cash flows, when we have our uniform cash flow problems or annuity problems, we can also use this closed form equation to help us out, where we say the PV tote, which would also be CF0, is equal to C times this whole mess, where this whole mess is defined like this. C is the periodic payment, which we have been calling on the other page CF. N is the rate, that's the interest rate or discount rate, right? And N is the number of periods, the number of times this constant cash flow gets paid out. And we've been considering that T, like 5 years, 5 payments, that type of thing. Okay, and we can use this first equation for any type of uniform cash flow project, including an annuity due, which we'll get to in a bit. And this one, equation 74e, I'll put that up here again for us just so it's very clear. That can be used for everything except annuities due. So you got to be careful about that. If you have an annuity due problem, remember not to use this formula because you'll get the wrong answer. Okay, so let's jump right in with an example. Let's look at a 3-year mortgage. So we've got out there Mr. Small Net Worth, SNW. Mr. Small Net Worth wants to get the biggest 3-year mortgage he can afford to buy the biggest shack that he can find. So he goes to a lender, and the first thing that a lender does, we've talked about this a little bit already, with any prospective borrowers, they say, how much can this borrower afford to pay back every month or every year without going bankrupt, without running into trouble? So that's the most important analysis for a consumer lender. And so they do that for Mr. Small Net Worth, and they figure that he can pay back about $12,060 a year without going bankrupt. They also have a policy that for borrowers like Mr. Small Net Worth, they charge 10% interest. So with that in their pocket, the next thing they need to know so they can tell Mr. Small Net Worth is how much will they let him borrow. So they want to let him borrow as much as possible. They think he's a good credit risk without having to pay back more than $12,060 a year, which might put him into bankruptcy. Okay, so let's think about a cash flow diagram for this. Remember, all of Mr. Small Net Worth's 3 mortgage payments are going to be uniform. So all the cash flows here are going to be identical. And we can see that really clearly in this cash flow diagram. And this is a cash flow diagram for, it could be either for Mr. Small Net Worth or for the lender. In this case, it's definitely for the lender, right? And you know that because the cash flow at t equals 0 is negative. Lenders lend the money, they take the money out of their vault and give it to someone. And then in the future, they get these positive cash flows in return. Okay. And so we know a lot about this one. We know that they're going to expect back 12,060 at the end of 1 year, 2 year, 3 years for Mr. Small Net Worth. And then all we have to do to find out how much they can loan him is take the present value of this one at 10%, the present value of this one at 10%, the present value of this one at 10%, and then add them all up. And that's going to be PV tote or CF0. So that's our mission. And to think about it in the terms that we've been using before, the lender wants to loan a tranche to Mr. Small Net Worth that's going to grow to 12,060 in 1 year for them, another tranche that's going to grow to 12,060 in 2 years, and a third tranche that will grow to 12,060 in 3 years, all growing at that 10% interest rate. All right, so let's see if we can solve this using both equations, 74D and 74E. So first up, let's go with 74D, okay? And we have 3 payments coming in, so let's take this summation notation formula and just turn it into a finite term formula. So we could say that this is equal to CF times 1 over 1.1 plus 1 over, that 1.1 is the 1 plus 10%, 0.1 squared, okay, plus 1 over 1.1 cubed. All right, and so when we have our 12,060 here, we already put in the R is 10%, we can say that the PV tote is equal to, so I'm going to solve this together with you using Excel. And we get 29.99. That's close enough to 30 for me. So I'm just going to say, let's call it 30. All right, so that's how much they can lend Mr. Small Net Worth for this 3-year mortgage. They can lend him $30,000 for this 3-year mortgage. So now let's go ahead and solve this using equation 74E. So we're just going to plug in everything here and solve it for us in Excel. So we have 12.06 times this whole mess. Type that out. I think you're going to get exactly this. And let me bring that into Excel for us. Okay, and we also get the exact same number that we got, whoops, with our other formula. All right, so you can use either formula you want there, and you'll be fine. So just a good time now for a little bit of review on time value and risk. As we've seen several times this semester, the interest rate or discount rate of a project increases with its risk. This is true not because it's a law of nature or anything like that. It's true because it's found to be true empirically. This is what we see in the marketplace, okay? So the implications of this are that the US Treasury, which remember is just about the safest borrower in the whole wide world, can borrow money at just about the lowest interest rates in the world. And so we're going to start calling US Treasury bonds risk-free investments. And subprime borrowers, who are sort of risky consumer borrowers, are going to be paying more interest than the Treasury, clearly, usually a lot more interest, to compensate for the higher probability that they may default. So let's just keep this all in our mind. as we go forward. And let's move on to financial annuities. So a financial annuity is a constant cash flow project or an annuity project where the borrower says, give me X now in return for an annual uniform payment of some other amount. And it could actually be annual payments or monthly payments or quarterly payments, doesn't matter, but always the sum of the repayments by the borrower better be more than the amount initially lent by the lender. So who's interested in these financial annuity products? Well, generally, they're good for retirees who want a guaranteed income of, say, Y dollars for N years. Also, they're good for consumers who think if they've got a pile of money X, they think that if they invest it themselves in the stock market, they might squander it, they might lose it all. So it sort of enforces discipline on them to say, okay, I'm not going to invest in the stock market. I'm just going to invest this all in an annuity, and at least then I know what I'm getting. So let's do an example here. So Velocity Advisors is back, and now they have a 3-year annuity offer. This comes with a 7% interest rate. And we want to know for this project, how much our customer is going to have to pay now, what's their CF0 going to have to be to receive Velocity's promise of 3 equal payments of $50,000 each at the end of 1 year, 2 years, and 3 years, right? So what we're gonna do with this, like we've always done, is there's gonna be a tranche that'll be growing into 50, a tranche that'll be growing into 50 after 2 years, and another tranche that'll be growing into 50 after 3 years, right? And that's gonna be, we could call that A plus B plus C, and as usual, CF0 equals A plus B plus C. Okay, so we're just doing repeated applications of the future value, present value formula to discount each of these back to t equals 0. We're going to discount them back at 7%. We're going to add them up. Right, and then we're going to say, like we said before, these are equal to our CF0. All right, so let's look at the solution for this one. So I take that first payment by Velocity of 50,000, okay, and I discount that back by 7%, just using the future value, present value formula, right? And so that's 50 over 1 plus 7% to the 1, or 46.73. Okay, I take the second cash flow, I discount it back by 2 years, right? And that gives me 43.67. And see, that 43.67 is going to grow at 7% into the 50,000 payment in 2 years. Okay, and then I take the third payment, discount it back, that's equal to 40.82, and then I add them all up, and I get my 131.22 CF0. So I add these three up, and I get my PV tote or my CF0. Okay. All right, so now let's think a little bit about annuity due projects. Annuity dues are annuity projects with repayments made at the beginning of the period instead of the end of the period. So in this case, we saw Velocity was making payments to its customers at the end of year 1, the end of year 2, the end of year 3. For a 3-year annuity due, they would make the first payment at the beginning of year 1, the beginning of year 2, and the beginning of year 3. So that's the difference. So you might be thinking, that's pretty weird. Why would anyone do that? Well, actually, they're relatively common for these reasons. Clearly, if you have an annuity due, the lender is going to get their cash back more quickly than they would with a regular annuity. And also, the borrower, they have this nice feature for borrowers and lenders, really, that the borrower is paying upfront in each period for the use of an item in the period. And this is exactly what we see with a lot of rental agreements and leases. So your rent is due on the first day of the month or the last day of the prior month, and that gives you the right to stay in your apartment for that month. So you pay first, then you stay in the apartment for that month. So that's an annuity due type of structure. So let's jump right in with an example. Let's look at a 3-year annuity due lease project. And let's think about a lessor's point of view, okay? So a lessor, one fine day, goes out and they buy a 7075 aluminum alloy 3D printer. 7075 aluminum is the best, strongest aluminum in the whole wide world. So if you can get a molten printing 7075 aluminum 3D printer, that's a pretty cool machine. So she pays $140,400 for this printer, and it's got a 3-year life, she anticipates. So why did she go out and buy that machine? Because she's a lessor. She's going to lease it to someone. So on the same day she goes out and buys it, on the same day she leases it to Green Car Company that we met in Chapter 3. She leases it to Green Car Company for 3 years via a 7% annuity due, i.e., this is going to be, from her perspective, she's going to call this a 3-year 7% lease. So let's see if we can find out what Green Car Company's annual payment is going to be for this. Start with a cash flow diagram. This is going to be really helpful. So this is a 3-year project, right? Because Green Car Company is going to have the use of this machine for 3 years till the end of year 3, right? So what we've got here is the lessor has paid $140 for this machine, okay? And she's going to get 3 equal payments back from Green Car Company of CF. The first one is going to be the same day. So for her, she pays $140,000 to buy the machine, to the manufacturer of the machine, but then that same day she's going to get CF back from Green Car Company. And that's going to give them the exclusive right to use this machine for year 1. And then at end of year 1, which is beginning of year 2, they make another payment of the same amount, which gives them the exclusive right to use the machine for all of year 2. And then they make a third and final payment, which gives them the exclusive right to use the machine for all of year 3. So all of these numbers I'm showing here are EOY. EOY 0 is at t equals 0, EOY 1, EOY 2, EOY 3. Okay, and as usual, we're going to have payment A, payment B, payment C, present valued, are going to add up to 140.4 here. All right, so let's use 74D. That's our summation notation formula to solve this. So that's going to look something like this. We just, as usual, take the CF out of our summation, okay? And now we have 1 over 1. Why 1 over 1 and not 1.07? Well, because that cash flow payment is made at t equals 0, right? She paid the 140.4 to the manufacturer, but she's going to get a payment the same day from Green Car Company. Okay, so that's our first payment there, plus 1 over 1.07, okay, raised to the 1, plus 1 over 1.07 raised to the 2. So this represents here the discounting of that final payment happening at end of year 2 that gives Green Car Company the exclusive right to use the machine for all of year 3. Okay, so now our cash flow is going to be equal to through the magic of algebra, 144 divided by this whole mess. So let's just solve this in Excel. I'll bring over the Excel window again. Okay, and we get 49.99 or 50,000. So let's put in here 50K. All right, so far so good. It's just very important to keep your wits about you and say, when do all the cash flows happen? So long as you do that, it's always going to work out just fine. Okay, so now let's think about general formulas for annuities due. So we've already seen we can just use our standard annuity formula to solve annuities due. Just be really careful about when the cash flows occur, and it's all going to work out just fine. Happily, we do have another closed form equation to help us solve these annuity due problems, and it looks very similar to the one we saw before for annuities, but it's a little more complicated. Thing you got to remember is this one works only for annuities due, so we're going to call this 74F. So let's apply 74F to our lease project example and just confirm that the formula works and we can get the right answer here. So let's give it a shot. Okay, what we're going to have here is our PV tote is equal to 140.4, and that's going to be equal to C or CF, either one, times this whole mess in here now with the numbers that we need, which are going to look something like that. And let me just go through a little bit of this with you. Key thing to remember here is that we're raising this to the -2. It's a 3-year project, but the last payment happens at end of year 2 to give them the right to use the equipment for year 3, et cetera, et cetera. Okay, so then we'll go down here and we'll solve it for our CF is going to be equal to 140.4 divided by that whole same mess. And let's bring this into Excel just to make sure I don't have a typo there for you. Hopefully not. Okay, and we get the same answer that we got from our general formula, which is exactly, of course, what we need and what we were expecting. Okay, so just quick heads up going forward, when the context is clear, sometimes we're just going to say PV instead of PV tote or CF0 in our multiple future cash flow problems, and that's just shorthand, so we know that that's going to count for the present value of every cash flow for the project in the future, first discounted, then added up. All right, next up is what we call the set of perpetuities. And perpetuities represent a class of problems where we have a uniform cash flow project, but the payments go on forever, out into infinity, out until hell freezes over, right? So what that's going to look like, modifying our formula 74E, is we just have our uniform cash flow out here, and now instead of stopping at some finite point, we just go out to infinity. But happily, this is really easy to convert to a closed form equation. And let's think about how this could work. Let's say we have $100 that we're going to invest in a bank account that pays 10% compound interest forever. But every year at the end of the year, we take out $10. Okay, so what's happened? Our 100 has grown to 110. We take out 10, we're back to 100. Next year, it's just going to grow to 110 again, and et cetera, and et cetera, et cetera. So if we live forever, that would actually be a perpetuity, right? And our principal is never going to grow or decline, and it satisfies our cash flow is just equal to the interest rate, 10% in this case, times the present value. So through the magic of algebra, if we solve that for our present value, we get the present value of a perpetuity is the uniform cash flow divided by the interest rate. So this is a formula that's good to know. It comes up in finance a lot. And another interesting thing about this is not just a mathematical thing that's used to prop up some theory or something like that. Perpetuities are real things in the real world. So I have a couple of interesting articles on perpetuities. The United Kingdom over the centuries has issued a bunch of perpetuities. So I have an article for us from The Guardian on when some of these were issued, and some of them had a call feature. They were going to go on into perpetuity unless the government called them. Called them means the government can put a maturity time on them when they want to. And some of them now from the 18th century are just being called, which is pretty interesting. And then we have an interesting article from George Soros on the case for perpetual bonds in today's economy and advocating that the EU issue some perpetual bonds. Okay, so let's jump back into our perpetuity thoughts here. So as usual, let's do a little example. Let's say a local bank will pay us $100 a year for our lifetime if we deposit $3,000 in the bank today. You're planning to live forever. That would be a nice thing. If that's true, what's the interest rate on this perpetuity? So if you live forever, but also don't forget the bank has to survive forever, right? They have to never go bankrupt. If both of those two things are true, can we figure this out? Yes. We'll start with the perpetuity formula, and through the magic of algebra, we will get that R is equal to our cash flow divided by our PV, and that's equal to 100 divided by 3,000, and that's equal to 3.33%. That's pretty good. Okay, finally for this chapter, some of you have been waiting for finally, I'm sure. Okay, the last thing we got to cover in this chapter is what's called a growing perpetuity. And a growing perpetuity is just like a perpetuity, but each cash flow grows a bit beyond the previous cash flow by this constant 1 plus G. So if we get cash flow C1 in year 1, in year 2, we're going to get C1 times 1 plus G. And in year 3, we're going to get our C1 times 1 plus G times 1 plus G, et cetera, et cetera, et cetera. Okay, and the mathematicians who are better at this than me have been able to prove that in this case, the present value of a perpetuity is equal to the first future cash flow that we're going to get divided by R. That's our interest rate. That would be what the bank is offering us, minus G. That's the growth rate, the annual growth rate of the cash flow. Okay, so good news about growing perpetuities. For those of you in finance, you should know this because it does come up in some advanced classes in finance. And for the rest of you, you don't have to worry about it so much. In this class, you need to know that growing perpetuities exist, but I'm not going to give you a numerical example of how to solve a growing perpetuity. And on that happy note, I'm going to call it a project for this portion of our lecture series, and I'll hope to see you in the discussion forums, office hours, and if not then, in the next video. Take care.